Hello, everyone. First of all, we would like to say thank you in advance for taking the time to listen to our presentation. As part of the Read Develop program hosted by the University of Calgary, we are a group of 3 graduate level students with a diverse educational background, and we were tasked with looking at the challenge of methane emissions in Alberta. To this end, we focus on the issue of surface casing vent flow emissions from a detection, quantification, and mitigation point of view. So today we are going to cover an introduction on methane emissions and give a primer on surface casing vent flows. Following this, we are going to look at climate change and how Indigenous groups, specifically members of the Métis Nation of Alberta, may be affected by climate change. After this, we will delve into our case study, which was focused on the Red Deer area, where we attempted to characterize surface casing vent flow leaks. Finally, we will look at some of the policy implications of surface casing vent flows from a cost standpoint. So looking into methane emissions in Alberta, we found there were many sources of emissions ranging from naturally occurring to anthropogenic, with the largest source in Alberta being from oil and gas, making up 45%, as you can see on the figure on the right. Of the oil and gas emissions, we found that surface casing vent flow emissions are a substantial contributor. But several challenges exist in knowing the exact contribution of any of these leaks due to intermittent nature of methane leaks. And that is a huge challenge, not only for the mechanics of detection, but also for the economics of detection. It costs a lot to deploy equipment long term, and occasional surveys may not catch leaks that are intermittent. Now the question is, why is methane such a big issue for climate change? Well, methane is really good at trapping heat. In fact, it is 29.8 times more effective at trapping heat than carbon dioxide, according to the latest IPCC report. So this is a big issue for climate change. Hence, the federal government wishes to reduce methane emissions by 45% by 2025, based on 2012 baseline numbers. So climate change exacerbation from methane emission is well accepted. So how does climate change affect Indigenous groups? Well, oil and gas exploration has occurred across the province for a long time, and many First Nations reserves and Indigenous communities and settlements host abandoned and active wells. These wells may be leaking methane to surface or potentially leaking into shallow water reservoirs. Although leaking methane may not have an acute health impact, climate change is a real risk, which is an indirect health hazard. To better understand how this risk affected an Indigenous group, we spoke with the Métis Nation of Alberta. What we found was that climate change affected the Métis community in a much deeper way than just economic and food security concerns. This beautiful image provided by the Métis Nation of Alberta Environment and Climate Change team really highlights the connection the Métis people have with the land and the environment. The Métis Nation of Alberta, its citizens on climate concerns, and found that preservation of the land and water was central to the culture and identity of the Métis. Climate change in this sense is not only an economic and environmental issue, but truly a social and cultural problem. To better understand how to try and prevent these emissions from occurring, it was important to understand surface casing vent flows. So what is a surface casing vent? Well, a surface casing vent is a vent that exists on all modern wells. This vent is left in the open position, allowing for an uncontrolled flow of gas to escape to the surface from the annular space in the surface casing section. Surface casing vent flows can be due to poor cement bonding, a lack of cemented interval, and are required to be reported to the AER. For our research, we had to pick an area to focus on. We chose the Red Deer area. This was for a couple of reasons. First, previous studies have indicated an underestimation of methane emissions in this area, with some estimations of emissions being up to 17 times higher than what has been reported in inventories. Second, the Red Deer area has been a historically prolific area with over 21,000 wells drilled since the 1950s. As you can see on the right, our study area is framed and is roughly 9,300 square kilometers in size. The black dots are oil and gas wells, and the red dots are wells that have had surface casing vent flow events reported. A total of 1125 surface casing vent flows exist in this area. Now, our objectives for this research were to examine from a technical viewpoint. Do wellbore characteristics contribute to the occurrence of surface casing vent flow leaks in Red Deer? And by characteristics, we mean mechanical characteristics, such as completion depth, well trajectory, and so on. Are flow rates controlled by these wellbore characteristics? And we also wanted to understand if any regulatory roadblocks exist that interfere with surface casing vent flow mitigation. So to answer technical questions, we used two sets of data, including AER vent flow and gas migration flow rates and methane isotope analysis. By applying these two sets of data, we were able to locate current and historical surface casing vent flow leaks, identify the geological source formation and depths of methane emissions using isotope analysis, evaluate major wellbore characteristics that may correlate with surface casing vent flows by adopting statistical approaches such as ANOVA or analysis of variance and t-test. So different sources of atmospheric methane have distinctive ratios of carbon-13 to carbon-12, depending on where the methane came from. We use the ratio number to figure the source of methane in Red Deer. The graph on the left shows the relation between formation of oil and gas and carbon isotopes, where red indicates deeper sources and blue indicates shallower sources of emissions. The graph on the right displays our study area methane sources distribution. And as you can see, most of the methane is coming from shallower sources, and only a few leaks in the central and north part of the study area are representing deeper gas. So from AER flow rate data, first we look at the spatial distribution of flow rates to see if there is any specific trend according to geographic locations of the leaks. Most of the serious emitters, any flow rates greater than 300 cubic meter per day, orange and red colors, are located in eastern portion of the study area. Looking into completion formation, the geological formation wherein drilling is completed and oil and gas are produced from, the band formation has been the most exploited formation in the region and consequently shows the highest rate of surface casing vent flow leaks compared to other geological formations. In addition, we looked into some wellbore characteristics such as wellbore status and trajectory. For wellbore status, three main status of active, suspended, and abandoned were considered. About 40% of wells with surface casing vent flow leaks are in abandoned state. Analysis of variance was performed to investigate any relation between flow rates and well status, and according to this analysis, nothing statistically significant was found. The same process was repeated for wellbore trajectory. including vertical, horizontal, and deviated. 77% of wells with leaks were identified as vertical, and no statistically significant relation between well trajectory and flow rates were found either. Eventually, we investigated age of the wells. As it was expected, 95% of wells with 10 years age or younger are in active state. Looking at the age and wellbore trajectory indicated that almost all wells with 10 years age or younger are horizontal. As multi-stage horizontal drilling from unconventional reservoirs has become popular in Western Canada and the Red Deer region in the last decade or so. We also analyzed the well age based on completion formations for the Banff and other formations. Most of wells completed within the Banff formation are older than 20 years, indicating older and vertical wells. Some of the main findings from our technical statistical analysis includes most surface casing vent flow leaks consist of shallow gas and flow rates are highly variable. Most surface casing vent flow occurrences are wells completed within the Banff formation. Wellbore status and trajectory did not have an impact on flow rates. The largest percentage of serious emitters, the one with flow rates greater than 300 cubic meter per day, are 20 to 50 years old. So for policy aspect of the project, we reviewed AER Directive 87, which covers surface casing vent flow leaks and well integrity, including 4 sections of testing, reporting, classification, and repair. We analyzed the AER vent flow and gas migration data flow rates, reported dates, and resolution dates, and provided insights for each section. So don't get confused. We are still in policy section. This is what happens when the team consists of 2 engineers and 1 scientist. Data talks, right? To begin with, the AER flow rate data was missing for 47% of the wells identified with surface casing vent flow leaks. This led to some uncertainty in our statistical analysis, both in technical and policy. Lack of data makes inventory of methane emissions difficult. We also believe this might be one of the causes of underestimation of methane emissions in the region. Therefore, more frequently testing and reporting can provide better quantification estimates. For classification and repair section of Directive 87, we analyzed leak spell in the study area. Leak spell is the time interval between when a leak is identified and when the leak is resolved. The average leak spell in Red Deer is 3.7 years, with a maximum leak spell of 20.4 years. By plotting leak spell versus the closing date in the region, graph A on the right, it can be seen that there is an overall increased trend in leak spell. To make sure that leak spell is not linked to drilling history in the region, we plotted wells completed in the area since 1984, blue line on graph B, and also frequency of wells with surface casing vent flow leaks, histogram here. As it can be seen, drilling peaked in 2005, and there is an overall decreasing trend since then, which is not in agreement with the increase in leak spell. Therefore, we concluded that these 2 factors are not linked. As mentioned previously, according to AER, surface casing vent flow leaks are considered serious when flow rates are greater than 300 cubic meter per day and required to be repaired within 90 days. However, leak spells are high and around 1453 days for non-serious, and this leads to high social costs and cumulative methane emissions. Therefore, we incorporated social costs of methane into classification of flow rates and repair. We built a financial model of social costs of methane for non-serious flow rates based on AER social cost of methane value in 2012, converted that value to $2022. In addition, we use the repair estimate per well for surface casing vent flow leaks based on AER 2016 value, converted that value also to 2022. Red dashed line on the graph here. As it can be observed here, social cost of methane, y-axis, goes up with increasing flow rate, black line. Combining this with the repair cost, we found a critical point, intersection, where flow rate is 107.9 cubic meter per day. This means for every flow rate greater than 107.9, the social cost of methane is going to be greater than repair cost. And this is an important factor that should be considered when defining serious and non-serious flow rates. We would also like to pinpoint some observations that require further investigation in the future, but they were beyond the scope of this project. First, we noticed that 95% of wells with surface casing vent flow leaks are drilled in monobore casing style, which means no intermediate casing, and only 5% in telescopic style. Does casing program control the potential for occurrence of surface casing vent flow leaks? This should be further studied in future. Second, as it was previously mentioned, there is no link between flow rates and wellbore trajectory. However, we knew that majority of wells with surface casing vent flow leaks are vertical. This is consistent with drilling history in the region. Horizontal drilling and multi-stage hydraulic fracturing operation became popular in the last 10 years in the region, and there are barely any horizontal wells prior to that, according to our histograms here. With that being said, we noticed that comparing horizontal wells, potential for surface casing vent flow leaks with vertical wells, 12% of total horizontal wells have surface casing vent flow leaks, while this value is only 5% for vertical wells. We performed some statistical hypothesis tests, and that confirmed that these two proportions are significantly different. We looked into this problem in more details, and we spotted a cluster of horizontal wells in the central portion of the study area. When we looked back into isotope analysis, that indicated these leaks are thermogenic, but coming from shallower sources than the target reservoir. This raised the question of, does hydraulic fracturing operations and fracture propagations into overlying formations provide a pathway for surface casing vent flow leaks? That we don't know, but requires further investigations in the future. To sum up our technical and policy data analysis, we should emphasize that flow rates are widely scattered in the region, and it is difficult to see any statistical significance between flow rates and well characteristics. However, surface casing vent flow are more observed in vertical abandoned older wells, completed within the band formation. To quantify methane emissions more accurately, surface casing vent flow monitoring, testing, and reporting should be prioritized. And we believe social cost of methane may be a crucial factor and requires to be considered when creating surface casing vent flow classification and repair economics. Last but not least, climate change can be considered a holistic problem for groups like the Métis Nation of Alberta. Thank you again for being here and listening to our presentation.